Hi. In this second part for examples in section 3.3, we're continuing to work with double quantifiers and predicates. So for question number 9, we want to formalize using quantifiers. And so we have a statement here, every positive real number has a square root. So the way that we want to do this statement is if we have if we have a predicate p of y, so that y is the square root of x, then we can write this as for all x that belongs to R plus, since it's positive real numbers, then we can write is this a y that belongs to the real numbers so that p of xy. And so in this way, I will be writing that y is so that y squared equals x. So this statement will generalize that idea. So is this a statement true? Yes, it is true. There's always going to be, for every real number, you can always pick one so that you can write y squared equals x, or y equals the square root of x. In particular, the positive root. Now, question 10 is about write the negation. Is this x that belongs to the integers? Is this y that belongs to the integers? So that x squared plus y squared equals 10. So if I'm going to negate this, once again, I start by negating the first one. These first exists for all x that belongs to c. Now I'm going to negate the second one for all y that belongs to c. And now I'm going to negate the predicate, which would be x squared plus y squared is different from 10. Now, is this original statement true? Is it false? Well, the answer is yes, this is true. In particular, you can pick x equals 1, and you can pick y equals 3. Oh, wait a minute. This is saying it says 1, right? So we just need to show 1. We're not proving the negation, but the original statement. So with the original statement, we just need to prove 1, and x equals 1, y equals 3 works. We get that 1 squared plus 3 squared is 1 plus 9, which is 10. So yeah, that works. Now, this is for the original statement. This is true. Now, for the negation, we gotta prove for all. And that's much more difficult to do. Okay? And since the original statement is true, then the negation is going to be false. Okay? All right, moving on. Question 11 is, for every real number, there exists an integer greater than it. So there's two domains in here that we got to pay attention, real numbers and integers. So for every real number, so for all x that belongs to R, then exists an n that belongs to the integers so that n is bigger than x. And this is actually true. In particular, for any x, you can always pick n to be the ceiling of x, which is the next integer close to x, plus 1. So that way, you can always get in the closest integer to n and then adding 1. And so with that, we guarantee that that's going to be bigger than x. Now, the negation of the original statement will be exists in x that belongs to R for all n that belongs to C, so that n is less or equal than x. And is the negation true? Well, because the original statement is true, then this is going to be false. Okay? All right, moving on. Question 12. We have negate the following statement step by step. So for all x that belongs to R, for all y that belongs to R, it says C that belongs to R, so that x plus y equals C. So notice that it has three statements, and we can negate all those. The negation of for all x will be in assist x that belongs to R. The negation of the all y for all y will be assist y that belongs to R. And the negation of the assist C will be for all C that belongs to R. And so the final negation will be just assist X that belongs to R and assist Y that belongs to R for all C that belongs to R, so that X plus Y is equal C. Is different from C in the final negation. Now we want to know if the original statement is true. And yeah, this is true. In general, for any two real numbers, x plus y is also a new real number. So that's that you can consider that your new C. And so x plus given x plus y belongs to the real numbers, and we can call C equals x plus y, and that is also going to be a real number that works. Now for question 13, we want to say true or false, and let's play the reasoning. It says for all x and y, for all x this is y, so the p of xy, and it says y for all p of xy always have the same value of truth. This is pretty much saying that it doesn't matter the order of the quantifier, that's going to be true. And no, this is not true. We have a counterexample of p of xy being y bigger than x. We actually saw this recently. So it's very different if I say for all x is equal to y, so that y is bigger than x, which will be the case of x plus 1. So that will make this one true. But for this one, we will be saying that it says a y that is bigger than all of them, and this is false. We saw this in a previous example. Now, if for all x this is y p of xy is true, then it says y for all x p of xy must also be true. Once again, this is going to be false, and we can use the same counterexample here for this. This is kind of an equivalent question somehow. This is a then, so that's the difference in there. This is a P implies Q situation. This is a P implies Q situation. And notice that if we use this same one, we will have a true implying false. And true implying false is going to be false. And so that make it so this implication is it doesn't have to be true always. Okay? Here what is going on is the rule of the implication, and remember, true implies false is false. The first statement is true, the second statement is false, so the implication is false. But that doesn't work as always saying that this implication must always be true. Now for C, say if the opposite, if it says y for all x, so that p of x is true, then for all x it says y, p of xy must also be true. And so if there is something that y that works for all x, regardless of what p of xy is, then it certainly is going to work. It certainly is going to work for each of the x. Okay. If this is one y that works for all the x, then for all the x that particular y is also going to work out. This statement is weaker. The second statement here is weaker than the first. This is much more stronger, and this is something that then is going to be an implication of the sort true implies true. If this is true, then by definition this will be true as well, and this is a true implies true implication, so this is going to be true. Once again, regardless of what p of xy is. All right, so now let's move on to question 14. So now consider every student has taken at least one math course. Is going to be or predicate. So txy will be a student X has taken course Y. So we want to write this using quantifiers. So that'll be every student. So for all X that belongs to the set of students, exists one Y that belongs to the set of courses, so that T of xy. So for all students, this is one course, so that student has taken that course. The negation will be is this, X belongs to S, for all courses, so that negation of T of xy. And translating this in English will be assistant student and this will be, since this is for all courses, this will be assisting a student who has not take any math course. Okay, remember the original is every student has taken at least one math course, but then the opposite will be assisting a student who has not taken any math course. Last, we want to formalize there's a real number that is less or equal than every other real number. So we will say assistant X belongs to R for all Y that belongs to R, so that X is less than or equal than Y. So here we will be saying this X is smaller or equal to Y for every other real number. Of course, this is going to be false. Okay? There's no number that is smaller than all the real numbers. This is the opposite idea of the bigger. And of course, in the same way that there's not a bigger number than every other real number, there's also not going to be a smaller number than every other real number. Okay? You can always find one that is smaller. For example, if I pick that number to be 1, well, there's always 0. If I pick minus 50, then there's always minus 100. There's always going to be a smaller real number. All right, this marks the end of the examples for section 3.3.